So let's talk about drag force. Let's talk about drag force. So the concept of drag force is when an object moves through a fluid. Key is a fluid. When an object moves through a fluid, it feels a resistive, viscous force on its surface. It's a resistive, viscous force that's physically acting on the surface of the object. There are a lot of things that go into drag force. We're going to write a formula down that kind of summarizes it for us, but there are a lot of parameters that matter. So it's not just when we're writing the formula. And there are two models of ways to look at drag force. One model is when objects are moving with laminar flow through a fluid. Laminar means streamlined flow. For example, something that is laminar flow would be low velocity, and the object itself would be a nice contoured shape, as opposed to something moving at high velocity, or an object that's a shape, maybe something like this, falling through the air. This object does not accelerate very much. Because of its shape and because it's very low mass, it reaches terminal velocity very, very quickly. So if we were to model this with a motion detector, we would see that right away. I mean, probably by the time it gets here, it's not accelerating anymore. It's moving at a constant velocity. So again, most things accelerate at a longer or for a longer time period as they fall because they're more massive. But if an object has a low mass and a lot of turbulence in the flow, then we'll say that it accelerates only for a small time period and it reaches a constant or terminal velocity very quickly. So the two models that we're going to look at, the first model is that the drag force is proportional to the velocity. And then the second model is that the drag force is proportional to the velocity squared. The AP exam can choose either of these models and it will state it. It will state which model it's using. And the model is dependent upon those parameters I was just mentioning. So slow moving objects, meaning laminar flow, low velocities, with objects that are streamlined in their shape, like a javelin that you would throw in Olympics, or a bullet, or a missile, those objects would really follow this first category here. And again, this first one is assuming that it's proportional to the velocity itself. In the second scenario, we're talking about higher velocities, more turbulent flow of the air around the object. For those, I mean, you all probably heard the phrase turbulent, but I know you didn't necessarily cover fluid mechanics last year. But turbulence has to do with the flow of the air around the object. And the way you can see that is if you've ever looked at a river or a stream, and when a current hits a rock or a boulder, after it goes around it, you'll see what are called eddy currents. There's little vortexes of water churning. That's turbulent flow. Or if you've been like on an airplane and you feel turbulence, that's turbulent airflow on the airfoil, the wings themselves. And that's the second scenario really when there's turbulence. So the first is low speed and mainly laminar flow. And the second is higher speeds. And these things go together, by the way. Lower speed is traditionally laminar flow anyway. Higher speeds and where it's more turbulent flow. Your text uses the second model with all of its work. So in all of these problems that we're going to do in your homework, we're going to use the second model. But the AP exam could really approach with either model. Just keep that in mind. And part of today's lab that we're going to look at is going to be studying the fall of coffee filters to determine which model fits. Okay, which model it fits. And D stands for drag. I'm going to write it, your book uses D. I'm going to call this F sub D. Okay, so when I write things, I'm going to use F sub D. Your book uses capital D, so I start with that first. Force due to drag. Force due to drag. The lab today that you're going to look at, I'm going to give you guys like a handout for it, uses R for resistance. It's the same thing as capital D, the same thing as F sub D. Now, the real formula, not just that it's proportional, but the real formula, or the more elaborate formula that the book uses is the following. And this is the one that we're going to really end up using, that the force of air resistance is equal to 1/2 C rho A V squared. Now, let's describe and talk about what these things are first. So C is called the drag coefficient. C is called the drag coefficient. What do you think that might be a function of? Say again? Surface of the fluid, but what about the surface? What about it would cause C to be different?
Like the density of it maybe, or
we're going to get the density of the fluid itself in a moment.
Composition of it.
Okay, composition of the object.
Viscosity?
This is actually going to be more involved with the object itself, but the viscosity does play a role here. I guess you're talking about of the air the fluid is traveling through. Yeah. Traveling through air versus like molasses.
Yeah.
So viscosity is a good way, yeah? Say it? It's like a lump friction parameter, good. So it's involving the air and the object itself as an interaction. But with the object, think about like its roughness of the surface, its not just cross-sectional area, but streamlined shape. Think about old cars. When Ford came out with cars, they were very what? What shape were the cars really? They were very what? What's the word you might use? Chunky, boxy, rectangular, right? And now you look at cars like Lamborghinis and cars that can get really high speed, they're not that shape, right? You know that? So this parameter C is in itself a lumped parameter.
The Cybertruck.
The Cybertruck?
Oh,
Oh, the Tesla? Yeah. I didn't know that was called. So this capital C is a lumped parameter. Lumped means it involves many characteristics. C is a result of many characteristics. It's a lumped parameter. You'll hear that phrase a lot in physics and engineering in college, lumped parameters.
Calculated benefits.
That's the thing. It's going to be given in problems. C is going to be a value that they're going to either give you or what you're going to do, Tristan, is you're going to be measuring all the other things and then determining C. So C is like mu. How do we determine mu? How did we do it? Or we only started that last lab. But in the demo that we did with the push card and stuff, how do we determine mu?
U equals tan theta.
That's the result for the inclined plane, absolutely. But I'm saying, like, how did we determine it? Did we say, let's solve an equation to get mu really? But we actually had to do what? We had to physically experiment to figure out mu. Mu is a value that you get as a result of experiments. That's what it is. Mu is not something I can be like, oh, plastic and metal, mu is 0.5, so just calculate it real quick. No, it's not. It's an experimental thing that you determine through trials. Same concept here for the drag coefficient. Although this value can be known for certain scenarios in tables, tables most likely come from experiments. So in your text, there's a table that gives you the terminal speed for certain objects. A parachuter, a raindrop, a ping pong ball, a basketball, a tennis ball, a baseball, a skydiver, and then a shot put. And it gives you the terminal speed for those. That terminal speed is this v that we're solving for in this equation, but it's most likely experimentally determined.
And isn't that like highly like subjective to the situation?
Of course.
Because like not all basketballs are the same. Like
Yeah, well, you mean for those objects? Yeah. It would have to be a control of some sort. But it is still highly subjective to the experiment itself, to a lot of different things that are interactive.
V is the terminal speed, right?
V is the terminal speed, yep. Or terminal velocity in this case. Terminal speed is fine here. Rho, anybody remember from my class last year what rho stands for? Yeah, and that happens to be the density of the fluid that it's flowing through.
is that just like a P?
It is. It looks like a P, but here's how it's drawn. Ready? Look at the top right of the board. You see how it's got like a curl to it? So it's the Greek letter rho, R-H-O, and it traditionally stands for density. In this case, it's the fluid density that the object is traveling through. Yeah.
It has units, right?
Rho does have units because it's density. So density is what? Mass over volume, right? So kilograms per cubic meter. Kilograms per, God bless you, per cubic meter. Let me just see real quick. Hold on, I want to make sure. I forget if C has units, but we can figure it out. We'll figure out if C has units based on dimensional analysis. A is the Now, the book calls it the effective cross-sectional area. Why do they use the phrase effective? Effective. What do they get?
Because like an object can be like curved or shaped, but it's just head on. Like
The cross-sectional area itself can vary. The shape may not be prismatic, so the shape may be tapered. So you might have something that has a higher cross-section area in the beginning and a smaller one later. So A itself is another interesting parameter. It's not just the cross-sectional area, it's the effective, meaning it can vary based on the object. It doesn't have to be like a slice of the object. Whereas if it was a bullet, the cross-sectional area is the same throughout all the parts of the bullet. You're literally taking a slice, and that's going to be that circular region you get. But the effective cross-section area has to do with objects that are not necessarily the same shape throughout their length. For our sake, we're going to say cross-sectional
so is it
area.
like a silhouette?
Yeah, it would be like that. It would be like a silhouette as a projection of that cross-section. But again, because shapes can change and stuff, we'll say it's an effective one. That's a value. What else? C, just to give you a value, usually ranges from 0.4 to 1.0. Kind of like mu varies, and mu is traditionally between like 0.1 and maybe a little more than 1, not much more. The drag coefficient, C, is usually between, again, 0.4 to about 1.0. Let's see. Yeah.
What does FO stand for again?
FD. Force due to drag. Due to drag. Sorry, it's a capital D. Capital D. Okay. Let's get into this then. So those are the general things that your book is talking about. Now, anything moving through a fluid exhibits air resistance. We've neglected it throughout the entire year. We've neglected it with projectile motion problems. But with forces now, we want to start considering it. So we're going to traditionally look at the free fall example for this. And your AP exam is definitely going to look at the free fall example. It could ask you multiple choice that has to do with an object traveling horizontally, and you're given a velocity, and you could find the resistive force acting against it. And if you know the mass, from F equals ma, you can find the resistive acceleration. So remember that if a projectile is traveling through the air, we've said ax is 0 all year. Ay is negative 9.8. But really, ax is a negative quantity because it's slowing down the motion. So if we can figure out the effective drag force, and we know the mass of the object, we can do this number divided by mass to figure out the net acceleration that it's feeling as it travels horizontally. But again, the mathematical problem, if it were at the end of the test and it has to do with drag force, will almost certainly be a vertical motion problem, because terminal velocity is the real concept that the AP exam tests you on with drag force. Okay, terminal velocity. Go ahead, sorry.
I was going to ask, like, if you reach terminal velocity, you really don't have there's no acceleration.
Correct.
In whatever direction the terminal velocity is, so how would there be a drag force that forces acceleration?
Terminal velocity only occurs vertically. Let's start with that.
Okay, yeah.
Horizontally, the drag force is just a resistive force, and it's the only force acting on you. So acceleration will always be negative horizontally. It'll always be acting against your motion.
Yeah, but like, how is it, so when it is hitting terminal velocity, how is there be a force if it's no longer accelerating?
Because gravity pulls you down always, and it's a balance. Let me draw the diagram for 1 second, then I think it'll alleviate this question. Okay, I get what you're saying totally. Horizontally is not the same as vertically, that's what I'm saying. So we're going to analyze it vertically, and you'll see why terminal velocity is in the vertical direction, not the horizontal.
So in like a vacuum, like space, there would be no terminal
Correct.
velocity.
There would be no air resistance in a vacuum. There are no particles because there's no fluid. The lack of air is a fluid. Remember, gases and liquids are fluids, both. Something that you might not have learned, you probably heard about in chemistry, but gases and liquids are both fluids. So if I rush my hand under water, or if I rush my hand through the air, I'm still feeling air resistance in both scenarios, or fluid resistance. I call it air resistance. It's just drag force. Yep, just drag force. So let's look at the vertical setup first so you can see this a little bit better. Okay, so let's say an object is falling freely and we wanted to draw the forces acting on it as it falls freely. We know that all objects have gravity pulling down on them. And in the very beginning of the fall, we have a little bit of air resistance. Okay, so here's where it's dropped from. Let's say that's the starting point right there at the top. And as it falls down, we recognize that it has some drag force. In the very beginning, it's only got its weight pulling down, right? We know that only weight pulls down in the very beginning. So this is like t equals 0, t equals 1. I don't know what 1 and 2 are. I'm not giving units of seconds. I'm just saying a next time period. After that time period, what will happen is the weight of the object doesn't change because weight is just m times g. That's never going to change. But the drag force is going to get longer. Longer, I mean the vector, sorry, is going to get longer. The drag force is going to increase in magnitude. Why is that happening? Because, again, here's my formula. My formula says F sub D equals 1/2 C rho A V squared. C isn't changing. Rho isn't changing. Well, actually, rho is changing. We'll get into that in a little bit. The density of air changes as a function of altitude. So, calculus-wise, this is really what we're going to see as like an integral later on. We're not going to have it in this course, actually. It's not going to be on the exam, so you don't have to worry. But really, rho does change. A doesn't really change when it's falling, but when it's falling, V changes. And V increases. As an object falls, acceleration causes the velocity to continue to increase. So if V is increasing, so is FD. If V increases, so does FD. So as this object falls further and further down, the vector representing FD gets larger and larger. It continues to get larger. But there's a certain moment where the force acting down and the force acting up are balanced. So my gravity is still going to be the same vector length. I'm trying to make it the same each time. This is my next time period. But at that moment, the drag force balances perfectly.
And FD can be greater than FG because FD is technically a function of FG acceleration.
Correct. FD, like the normal force member can never exceed the weight acting down unless you're pushing out the object. But for a free object, here's the same concept. If FD were greater, it would start to accelerate which way? Yeah. And because the velocity is now constant, FD can't get any greater. This whole idea is that velocity reaches a constant at this moment because it's no longer accelerating. And why is it no longer accelerating? Let's look at our equation of motion for each of these. At time equals 1, we've got FD minus FG equals MA. Well, it's still accelerating at time equals 1, so that equation holds true. At time equals 2, we've got the same exact equation again, because it's still accelerating at time equals 2. But when we get to time equals 3, suddenly it's no longer accelerating, so that goes to 0. Which is what allows us to make this conclusion right here, that the drag force is balancing the weight acting down.
Would there be problems where there's like a fan or something under the object, and then like a ping pong ball?
Like the hairdryer example,
Yeah.
Did I see that one? Would there be questions like that? I guess theoretically, because if you know the velocity of the air moving across the ping pong ball, it's as if it's the velocity of the ping pong ball moving through the air. Think about that for a second. If you guys have, I don't know if you've seen this example before, I can show you if not. Take a hairdryer, put a ping pong ball above it and hold it there. It has to do with the pressure along the sides, really. It's a Bernoulli's principle idea. But the concept of air flowing over the ping pong ball is drag force. It's as if the ping pong ball is falling down through the air. So if you had a fan, right? And you've seen this before, they have one in Maryland. It's a skydiving zone.
Yeah,
It's a giant fan at the bottom, and you're literally just like floating pretty much. What are they doing in that circumstance? They're taking the fluid flow, the fan pushing up, the force of the fan, and they're causing that force to be enough to balance your weight. So the example you just said is simulated skydiving. That's what it really is. So people that want to like learn how to skydive or practice it and stuff can go to these centers. I actually, this weekend it was passing, and I wanted to go actually. I'm trying to get my fiance to go, and she wasn't willing to go. Next time we do it. But yeah, it would be a lot of fun because you can like actually change your elevation and height based on certain things. So as your body moves and stuff, you start to move. There's a scenario, there's a story, and it's a true story, of two parachuters, two or three, whatever. There were a couple parachuters going down and falling toward the earth, and one of them actually on the way down lost consciousness. And the other parachuter noticed this, and the person was just flopping around. And they would just die, obviously, if they hit the ground like that, right? So the guy, it was a guy, the person who lost consciousness was like his friend or something like that. This guy actually went from being like in a normal position or whatever you'd be skydiving to purposefully diving, like reoriented his body to become more streamlined, like a bullet or like a missile, caught up to the person because the person was just tumbling, and when something tumbles, there's a lot of air resistance because it's constantly changing its orientation. Caught up to the person, got below the person, this is true, I'm not messing around, but you can look the story up, and actually caused his body to become more horizontal. So he increased the cross-sectional area of the flow hitting his body, instead of it being a very small area like when you jump in water in a pool and you die and go in like that. But if you belly flop, you really don't go far, right? So he pretty much like got underneath the person, caused his body to be horizontal this way, like this, slowed down enough to grip onto the person, right, holding them, reoriented both of them, pulled the chute on the person, and then himself continued going and then pulled his own chute. The person lived, but got a lot of injuries because it was a female. She was still unconscious the entire time. So he was able to pull her chute, but she never regained consciousness, but landed with much less velocity than she would have, but had a bunch of internal injuries. Survived, lived and all, but because the guy was able to catch up on the way down. Pretty crazy stuff. You've seen it like Mission Impossible kind of movies and stuff, right? Yeah. And it's like, oh, it's not, it really did happen. There's a whole story, there's a news article about it, yeah.
There was like someone else like similar to that, but like it was just like someone by herself, and she passed out, and she hit like an anthill though, and like the ants stung her so many times that the adrenaline in her body was able to keep her heart pumping long enough that she was able to go to the hospital.
No freaking way.
Yeah.
Oh, really?
Yeah.
Really? That's
So
incredible.
like a red anthill, and I think
They just kept biting her, so she was like conscious because of that?
Yeah. But I don't know if she was conscious, but like the adrenaline kept her heart beating, like instead of like the whole shot.
That's incredible.
That's just like the worst combo ever. Falling
You
60
can't move,
feet.
you're paralyzed, these ants are biting you.
Yeah.
Alright, so this is the concept, right? This is literally it right here. This is what we're going to be solving. So let's, on the next slide, write our equation for FD. FD is 1/2 CPAV squared, C rho AV squared. And weight is mg. Alright, and weight is mg. So that's where the equation becomes. So whenever you want to solve for terminal velocity, you're just solving for v in this equation. And again, this is based on the textbook's equation that is used. I'm going to talk about how the AP exam can vary in a moment. So this is going to be 2mg divided by c rho a all under square root. Okay, solve for v. Please just solve that for v. C rho a is divided, and then get rid of 1/2 by multiplying by 2. So that's our general equation for terminal velocity. And on the AP exam, they'll probably write v sub t, so you get used to that for terminal velocity. All right. How would they put it on the exam? So, on an AP exam, what they traditionally do is this. They say that the force of drag is equal to kv squared. Or they say that the force of drag for Model 1 is just kv. They take the 1/2 c rho a and make that a lumped parameter. So again, although 1/2 c rho a are all values, on the AP exam they have a tendency to lump those into a parameter that they call k. And it's an overall resistive coefficient. It's the overall drag or resistive coefficient that incorporates that c value, which is already a lumped parameter, right? So this is kind of ridiculous when you think about it. It's oversimplification. Because c itself is already a function of several things. Rho is the air density, or fluid density, which is actually changing as you fall. A is the effective cross-section, which could also change. So we're noticing that these are all variable parameters. So instead of having to worry about all the variable parameters, on the exam, you'll see it written on the top right that way. Your text, Halliday uses this equation, and then therefore uses this. But if I wanted to do it that way, the only thing that changes is that kv squared equals mg now, instead of this whole thing, right? We're replacing that whole thing with kv squared, and then v is just mg over k square rooted. And that's terminal velocity if you were to solve it using the formula with fv equals kv squared. So again, k is this thing circled in red here. And that's what you would get as a result.
So you would have to know, oh sorry.
That's okay.
You would have to know that k is equal to 1/2 c rho a.
They would ask you to either determine k or give you the effective coefficient as k, but you should know that it's made up of the drag coefficient, the fluid density, and the area of the object. This could show up in like a multiple choice type thing, where you need to know what parameters affect their resistance. These are the parameters. But if you're doing a problem mathematically on the test later in part 2, they'll most likely use this formula over here. And a lot of the old exams have that formula if you look at it. Okay? And sometimes they'll use kV. They'll say it's a very slow-moving object with a lot of laminar flow, so we're going to use FD equals kV instead. And then what happens is you just solve for V, and it's mg over k instead of square root. There would be no square root, right, if this wasn't square. That's the only real difference there.
I just have 2 quick questions. Is the units meters squared?
What units, sorry?
Area?
Yeah.
Okay. And then for kV, would it be 1/2 c rho a v?
The value k is 1/2 c rho a. Is that what you said?
So the difference between kV and kV squared, like for FD, you're
K is the same in both cases. Yeah, it's the same in both cases.
okay.
Yeah, it's a matter of just whether the flow is laminar, turbulent, and the speed of the object moving. But K is not, I know what you're saying, but you're like, K's unit's going to change, right?
Yeah.
Yeah, that's fine. That's totally okay. Okay. Because V's units are meters per second, and we know force is kilogram meter per second squared. So K, in the first case, would be kilogram per second. Right? Yeah, it'd be kilogram per second. And in the second scenario, it would be kilogram over meter. Yeah, the K units will change based on the 2 equations, but that's not more realistic.
The 1/2 c rho a won't. The general formula won't change between the turbulent and laminar flow.
Meaning this one here,
Yeah.
it actually, the units of C would change.
Not
That's
the
what you
units,
said.
but like just the general.
This would be the general form. Yeah.
Okay.
And then those are more of the simplified versions of that. Yeah, I get what you're saying. The units do matter, and in this case, that would be a different unit. That's okay. What is it doing? Sorry, it should be unlocked, guys. Sorry about that. All right, let's take, I guess, do we have an example? We could do one quick example of this so you guys can see it, right? All right, so a quick example here. I mean, the example in the book is just too easy. It really is. It just has you calculate terminal velocity. So you're just plugging in the parameters. I'll read it out to you so you understand what it would say. It says a raindrop with a given radius from a cloud falls from a given height. The drag coefficient C is given as 0.6. So they're giving you C right away. The drop is approximately spherical. So what do you need to know? You need to know the cross-sectional area of a sphere, which is what shape? A circle. So the area would be pi r squared. The density of the fluid it's flowing through is given as 1.2 kilograms per cubic meter. That's air. And then it's just asking you to figure out the terminal velocity based on all of those parameters. So it becomes really just a plug and chug. What I'd like you guys to rather see is how these parameters affect things. So let's quickly look at that. So let's write down our terminal velocity formula. So it's 2 mg over C rho capital A. So something to recognize and to notice in your book is going to ask you about this is going to say like, well, what happens if the area doubles? Or what happens if the density triples? Or what happens if the mass of your object doubles, right? So based on this formula, let's talk about those things. So if mass were to go up, what happens to terminal velocity? What does it go up by? So if mass were to double, for example, if mass were to double, what would happen to your terminal velocity? Yeah, it would go up by a square root of that value. So if I had an object that's twice as massive, and I wanted to compare those velocities, the velocity of object 1, that's smaller, times the square root of 2 would equal the velocity of object 2. So again, if mass 1 equals m, and mass 2 equals double that value, how does this really change is what's happening? So if you double the mass, your terminal velocity goes up, but only by a factor of radical 2, because this is directly related to v, but it's under a square root. The opposite is true for all of the denominator parameters. So if the density doubles, right, the density of the air physically doubles, the velocity goes down by a factor of square root 2. The second velocity, v2, or the terminal velocity of the second object, would equal the terminal velocity of the first object divided by square root of 2. So I'll write that second scenario down. So that was the first scenario. Oops. The second scenario would be this. If the density in the first scenario is listed as rho, and the density in the second scenario is listed as twice rho, then the velocity in the second scenario equals the velocity in the first divided by the square root of 2. Okay, what am I doing? I'm literally putting in 2 rho right here. And by putting in a 2 rho and thinking about what's happening to v, I'm having to double the denominator, but it's under a square root. So it's like putting a 2 in the denominator, but underneath the square root. And physically think about what's happening. The terminal velocity in the second scenario is less than the terminal velocity in the first scenario, because the air is more dense. More dense, it's not the same, but you could think of as more viscous for the purposes of this scenario. Honey versus water, right? Your hand through water would be viscous, your hand through honey and molasses would be really viscous. So that's what I want you to start thinking about when it comes to density. Area makes sense too. Use logic here, right? We just talked about the example you dive into a pool. When you dive into a pool, your cross-sectional area that hits the pool is the top of your head and like the projection of your body. But if you did a belly flop and you hit the water, you slow down much quicker, right? You reach terminal velocity really quick. So your terminal velocity is a lot less if you have more area. Again, area is in the denominator. And then C is the drag coefficient. The more drag you have, the quicker you're going to reach terminal velocity. Meaning terminal velocity, again, will be a lot lower. So if any of the denominator's parameters go up, you're going to have a much lower terminal velocity, which means it reaches that velocity very quick. If I have a higher terminal velocity, it takes me a longer time period to reach that higher terminal velocity. And that comes from having more mass. So those are the 4 parameters that matter. G is not going to matter as much because for these types of problems in the AP exam, it's definitely going to be on Earth. So these are directly related, and then these 3 are indirectly related. Okay, those are the parameters that do matter when it comes to understanding the conceptual part of this concept. All right, I'm going to stop there and have you guys start in the lab. I want to talk about it for a little bit. So I'm going to open up the lab on mine.